let's continue working on our test 2 review. We have a test next week. Okay, and this number 1 was the material for this number 1, something we learned last week. I will give you like approximately maybe 10 minutes to do this problem, but let's summarize what we have here. According to Real Clear Politics poll conducted in October 2015, 42.3% of voters in favor of Affordable Care Act. That's 42.3%, or in decimal, that's 0.423. And 49.5% opposing, that's 0.495. And the one without opinion, then that will be 1 minus the sum of those two. That is equals to 1 minus 0.918, that's 0.082. Now use this information to find A, B, C, D, and E. Let me give you 10 minutes. So I'll be back in at 8:33. Okay, let's start. I know you may not be done yet, especially if you just come in. Let's do it. Okay, part A. Of 35 voters, find the expected number of voters in favor of ACA. I will use blue color for the things you don't need to write in your test, but I write it here just to clarify what random variable we're dealing with. X subscript A here is binomial, number of trials 35, and probability of in favor of ACA is 0.423. So the expected value, either you use EX or you use mu, that's equals to N times P. That is 35 times 0.423, that's 14.805. Oops, sorry. I said the blue one you don't need to write in your test. But the one I write in black, you need to write in. 35 times 0.423, that's 14.805. Yeah, I write that the distribution notation so that you know what kind of distribution we are dealing with. Because you see, in part A, we deal with 35 voters, but in part B, for example, we are dealing with 60 voters. Okay, part B, of 60 voters, find the standard deviation of the number of voters opposing. So of 60 voters, the one opposing is 49.5%. This is the probability of opposing. So what is the standard deviation? Let's find the variance first. The variance will be N times P times Q. Okay, and Q is 1 minus P. Okay, 60 times 0.495 times 0.505. I get 14.9985. That's 14.9985. Therefore, then the standard deviation will be the square root of that number. Square root of that number is 3.87279, and make it in 5 decimal places. Okay, make it in 5 decimal places. Part C, find the probability that of 8 folders. So now my number of trials is 8. At least half of them in favor of ACA. In favor is 0.423. So probability at least half. Half of 8 is 4. Half of 8 is 4. So at least 4. Right? At least 4 means start from 4 all the way to 8 in this case. At least 4. Okay, so the complement is up to 3. Right? So this would be 1 minus probability that, let's see, is less than equals to 2. Then this is 1 minus binom CDF 8 0.423. I get 1 minus 0.54030, which will give me 0.45970. That's for part C. Go on to part D. Find the probability that any of those 8 folders, any means at least one, any of those 8 folders have or has or have no opinion. So even though we are still dealing with 8 people, but the one we are measuring right now is the one without any opinion. So it's another random variable, 0.08. Okay, the one no opinion, right? Okay, then probability that the number of people of this 8 that is no opinion, at least one, that's equals to 1 minus probability that none of them have no opinion. It's 1 minus binom PDF. Actually, when it is equals to 0, when it is 0, it's the same to less than equals to 0. So you can use PDF, CDF if that's happened to be 0. Okay, that's 8, 0.0820. That would be 1 minus 8, 0.0820. That's 1 minus 0.50436. That's 0.49564. Okay, last one. Of 60 folders, find the usual interval. So we have 60 folders, usual interval in favor of a foldable here X. Then XE, oops, the random variable we are dealing with is binomial distribution, number of trials 60, in favor is 0.423. The expectation, the mu is 60 times 0.423. I'm sorry, not 423. Oh yeah, that's right, in favor. Okay. 423, that is 25.38. And then the variance is 60 times 0.423, that's the P, times 0.577, that's the Q. It's 14.64426. Therefore, the standard deviation will be the square root of that. That's 3.8267. Now then, for us to find the usual interval, we see the lower fence is the mean minus twice the standard deviation. Let's see what's that. Okay, 17.72644, and the upper fence is 25.38 plus 2 times 3.82678. That is 33 something. So the interval is the usual interval is given by 17 point something up to 33 point something. Okay, that's for number one. But some warning though, some warning. Here, even though from what I do here, even though we actually have trinomial here, not binomial. Originally, we have trinomial in favor of, oppose, and no opinion. But the way the problem being set up, the problem being set up, at every question we focus only on the one in favor. Okay, so the one in favor will be opposed to the one not in favor. Okay, the one opposing, okay, or no opinion, right? Now, why I want to emphasize this? Because the following, it depends on the question, not depends on the situation, if a distribution being binomial or not. Okay, so sometimes the situation seems to be, oh, you know what, that's binomial, but when you look deeper into the question, it's actually not. You see, like in this case here, the situation given to us seems to be not binomial because it has three possible outcomes, right? But when the question comes, it's only focusing on, is it in favor, or is it opposing, or is it no opinion? And actually, we can go even further that in my old tests, I use the word not in favor. For example, the phrase not in favor. Now, the phrase not in favor is not the same to opposing. No, it's not the same. Okay, not the same. To be more precise, when we say probability of opposing here, just for example, the probability of opposing here is 0.495, right? Okay, you see up here, right? Probability of opposing. Okay, but probability of not in favor, the probability of not in favor is actually 1 minus probability of in favor. Okay, That's 1 minus 0.423. That's 0.577. Okay, pictorially, right now we have three situations. I can try to represent that with three boxes. That's the one in favor, that's opposed, and this is no opinion. Okay. Now, when we say opposing, it refers to this one. That's opposing. Now, when we say not in favor, it's basically not the one in favor, which may mean opposing or no opinion. Okay. So simply because somebody say, for example, simply because somebody say that person is not for Biden, for example, doesn't mean that person is for Trump. No, it's not. Okay, at least not that. That's not the direct consequence. It may be an indirect consequence, but that doesn't mean that person is supporting Trump. No, it's not. Okay, in fact, uh, the reality is this is the true one, that we have more and more people not in favor of both of them. Okay, Biden and Trump. Okay, so saying somebody is not in favor of Trump, for example, doesn't mean it implies that person is for Biden. No, it doesn't. It doesn't directly mean so. Okay, we have more when more people actually have hard time to choose among these two. Okay, yeah. So then this becomes uh, how to say that, this becomes a way some journalists then try to argue their case. So instead of saying that uh, uh, for example, Biden supporters is not increasing, they will say that the one opposing, not supporting Biden is not decreasing. Okay, so instead of referring to these, it refers to the whole these. You know, okay, that's how they may argue. So when you read news, be more critical on the way they say things. Now, the sad thing is journalists recently actually also have issue with their own reading comprehensive, therefore it will affect their writing comprehensive. Okay, they write one thing, but it means something else. Okay, be aware with that possible situation. You know, but that one we have no help though. We have no way to actually measure if that person write this means that. You know, okay, we need to judge somebody from based on what that person write. Okay. Number 7, I skipped to number 7. Yeah, last week we did number 2 to number 6 already. Okay, number 7. A store sells a certain type of bulb in packages of 25 bulbs each. The probability is 5% of a given bulb being defective. So let's say X be number of defective bulbs in a package. This X will be binomially distributed, number of trials 25. Probability of being defective is 5%. So part A, find the probability. What is the probability that a given package contains any defective bulb? So X is at least 1. That's 1 minus probability that X equals to 0. No defective, right? 1 minus no defective. That's by 1 minus binomials PDF 25 0.050. That's 1 minus 0.27739. Oh, that's a big probability. 0.72261. That's the probability of at least one defect. Part B, what is the probability that less than 3? Less than 3. Less than 3. It means I need to do adjustment here. It means from up to 2 only, right? That's binom CDF 25, 0.052. We get 0.87289. Maybe including 0, right? 0, 1, or 2. Part C, what is the probability that between 2 to 5 bulbs inclusive will be defective? Probability that X is between 2 to 5. Between 2 to 5. If you want to do it slowly, then you will compute probability that X equals to 2 plus probability that X equals to 3 plus probability of X equals to 4 plus probability that X equals to 5. I think that would be a bit too slow. Now instead, if we picture that, the possible outcomes, you want from 2 to 5. Okay? We want from 2 to 5. What we will do, what we can do is, we grab the cumulative up to 5, and then subtract the cumulative up to 1. Okay, so the second method I can offer you is probability that up to 5 minus probability up to 1. That will be faster. Okay, that is binom CDF 0.5, 0.055 minus binom CDF 25, 0.051. And when you use your calculator, please give the number for each first before you subtract. This is 0.99879 minus 0.64238. So 0.99879 minus 0.64238 will be 0.35641. Okay. Now I use different color, black and blue here, to show you that there are two different ways to do it. I'm not saying that the blue one is not how you will write it. Okay. You can do it the first method, but I think it will take too long. Okay. And the second method, in my opinion, is more effective. Now, part D. If a customer buys 10 packages, how many of the bulbs can he or she expect to find to be defective? 10 packages. How many light bulbs? 150? Right? So our our distribution now is binomially distributed 250 bulbs instead of only 25. Okay, probability of being defective is 5%, so the expected value will be 250 times 0.05. Okay, so 5 times that would be 12.5. Okay, that's for the partial review in my test 2. Now, the thing is, I need to warn you again that warning, Poisson distribution will be in your test 2. While it was not in my old test. Okay, basically you will study that on your own, and that's one of the reasons I give you that that assignment that you will supposed to do today. Okay, so that you have your own exposure to Poisson distribution. Okay, let me start with the lesson for the day. We will do chapter 6, and I actually plan to do 6.1, 6.2, 6.3. On 6.1, that's 6 standard normal distribution. I expect to spend approximately 1 to 1.5 hours here. Okay, now and then in 6.2 later on, that's normal distribution. That's not standard one, but normal distribution. I think I will spend approximately 1.5 to 2 hours here. Now the thing is, I need you to be pretty strong with standard normal distribution before we really get into 6.2. Okay. Now, what is standard normal distribution? Standard normal distribution is a continuous distribution that looks like this. This is a new way, another way to deal with distribution that is continuous. Okay, standard normal distribution, standard normal distribution is a continuous distribution. It is a continuous distribution and with curve having the following characteristic. First one, it's bell shape. Symmetric with respect to 0. It's symmetric with respect to 0. It's bell shape. It's bell shape, symmetric with respect to 0. Now you will see that this 0 here, to which it is symmetric, is the mean of that standard normal distribution. Okay, and when we say bell shape, it actually has the following meaning. It means that the further you are from the mean, the less likely for you to happen. Okay, the effect will concentrate around the average. Okay, and the chance that it goes further away from the mean, let's say the C score, the standard normal score is 3 or 4 or 5, it gets less and less. Okay, it gets less and less. Basically, when we say bell shape, is that the further you are away from the mean, the less likely for that event to happen. Okay, not only that it is less likely, it gets less likely faster. Okay, so you can see, for example, for this one here and this two here, it's not even one half. The two here is not even one half of that one. Okay, the three here is supposed to be 1/3 of one, right? No, it's not. It's not 1/3 of one. It's not even one half of that two. The height for two here is not even one half of that. So it actually dies down really, really fast. Okay, it dies down really fast. Now I will explain further into that. Okay, second, the area under the curve, the area is 1. Okay, now by the way, if I zoom this, the curve here is actually not dying down to 0 though. It's very, very close to 0, but it's not 0. Okay, now the total area under this curve, even though it's very, very thin there at the tail, the total area under the curve is 1. The total area under the curve is 1. Now, because of that, then we can tell directly that the total area under half of the curve is 1/2, right? The area here is 0.5. And the area here is also 0.5. Okay. Let me write it down as the consequence. Consequently, the area to the left and to the right of 0 is 1/2 each. Now then, the third one. The probability of an event, the probability of an event is equal to the area under the curve of that event. Okay, I guess I will give you these three characteristics first for standard normal distribution. Now, standard normal distribution is the most important distribution in probability and statistics. In fact, without standard normal distribution, there's no statistic. The reason you need to take this class because somebody in the past have nothing to do and discovered this standard normal distribution. And because of that person invented standard normal distribution, or to be more precise, recognize this pattern, then he developed statistic. And because of that person's fault, you need to take statistic right now. Otherwise, you are already transferred, right? Okay. If we try to say that way, okay. That's how important is this standard normal distribution. Because of this standard normal distribution, then all of a sudden we have a course named statistic. And the good thing is this becomes one of the building block of statistics. Now, saying it this way, I try to emphasize how important this distribution is. In fact, it is so important such that standard normal distribution is the only distribution to which a random variable is assigned to it. And it is random variable capital C. Okay, it's so important such that every time you see capital C, it means standard normal distribution in any probability and statistic textbook. Okay, every time you use capital C, it means standard normal distribution. Okay, and you are not allowed to use capital C if it is not standard normal distribution. Okay, people won't blame you if you use, let's say, oh, you know what, let X be binomial distribution, or let Y be binomial distribution, or let M be binomial distribution. Okay, you can assign any random variable, any capital letter for random variable, but you cannot assign this one. Okay, this is a big no-no. Okay, you cannot use capital C other than for standard normal distribution. Okay, that's how important it is. It's so important such that it deserves a special name that you don't assign to other random variable. Okay, so you use capital C only for standard normal distribution. Now, how do I explain then the third part here? Probability of an event is equals to the area under the curve of that event. Let's say, for example, part A, find the probability that Z is less than equals to 1.23. That's the probability notation. Let's take a look on what it means on the curve. 1.23, it's slightly over 1, right? This is 1.23. Okay. Now, probability of that event that we are looking for is equal to the area under this curve. Now, your calculator cannot compute the probability of an event. However, our calculator will be able to give you this area. Okay, now let's grab your calculator, TI-84, I assume, even though TI-83 will function the same way in this case. Now, where do we find standard normal distribution? We will do the following. Standard normal distribution is basically normal distribution with mean 0 and standard deviation 1. We get it from second distribution, the same way we get binomial and Poisson. Okay, now, but we will do normal CDF. We'll do normal CDF. Okay, it will be normal CDF. The notation will be, you need to see this event in an interval using interval notation. Now, for that interval notation, okay, the first number will be the lower fence. The second number will be the upper fence. The third number will be the mean. The fourth number will be standard deviation. Okay, now C distribution, standard normal distribution, is normally distributed with mean equals to 0 and standard deviation equals to 1. Therefore, the variance equals to 1. Okay, write this down first. Write this down first. Now, in intermediate algebra, you learn that this blue interval here, is denoted in interval notation is negative infinity up to 1.23. That's in interval notation. Okay, now that's the interval we will put here. Okay, that's the interval we'll put there. Now the problem is on our calculator we do not have negative infinity. We do not have negative infinity. You will also see later on we don't have infinity either. So instead of using negative infinity in our calculator, later on we will use a very big number in place of infinity, okay? And it is negative 10 to the 99, okay? Which in our calculator, they will use negative E 99. Okay, that's how we will replace negative infinity by, and therefore infinity will be 10 to the 99, or on our calculator it will be E 99. Yeah, right, E 99. So the thing is, like, for us to do this problem, we need to know first the calculator notation. That's normal CDF. Okay, what are the numbers you put in what order? Okay, the first two numbers is the interval for that event. Okay, the last two numbers is the mean and standard deviation. Okay, so for this one here, for this question, my lower fence, I will replace it by negative E99. The negative you use, always this negative. Take a look on your calculator. The negative you use will be the negative sign between the decimal point and the enter button on your calculator. It has to be this one. Okay, negative. And the E is not this E here. No, not this E, not this E. It's this E. It's written as double capital E, but when you punch it, it is actually means exponent with base 10. Okay, that's second E. So you see it writes EE, right? But when you punch that, it shows only E, 99. That's how we replace our negative infinity by negative E 99. Now the upper bound is 1.23. I happen to have it here. Okay, the mean is 0, standard deviation is 1, and then you paste it. Okay, now you will see if I trace back here, normal CDF, the first number is negative E99, second number is 1.23, the third number is the mean, 0, the fourth number is standard deviation, and then you press enter. Okay, so coming back here, this will be normal CDF negative E99 1.23 0 1 which will give us 0.8 something, I remember earlier, 89065. 89065. Okay, the probability notation, then you try to figure the curve first, and then the calculator notation, and then the calculator result. In your test 3, this is not in your test 2. Chapter 6 is not in your test 2. Chapter 6 is not in your test 2. Okay, it is in your test 3. So in your test 3, you will give me this one, this one, this one. Probability notation, calculator notation, then calculator result. The curve will be useful, okay, if you can do it, but if not, if you're already able to illustrate that in your mind, then you're fine. You don't need to give it to me, okay? For the first 1 hour today, or maybe the 2 hours, I will always give you the curve so that we can visualize the situation, okay? Now, let's see. Let's do more. Part B. What is the probability that C is less than equals to negative 2.7, maybe 2.53. Z is less than equals to negative 2.53. So let's say this is our standard normal distribution. Okay, negative 2.53 is approximately here. Right? Now you need the area to the left of that. Now the interval notation of the interval notation for that interval will be negative infinity up to negative 2.53. Right? But on our calculator later on, we need to adjust that to negative E99, negative 2.53. Okay, so when I write the calculator notation, that would be normal CDF negative E99 negative 2.5301. Then I use my calculator, normal CDF. Okay, that's the second option in your distribution. Negative E99, I already have it. Let me show you how to punch it again. Negative, it has to be the negative sign next to enter. Okay, don't use this subtraction sign. Once you use this subtraction sign and then you press enter later on, okay, when you try to uh, uh, paste the formulas, the output will be error. Let me show you. Let me show you. Suppose I use negative E99, right? Okay, it will be error. Do you see that? Okay, because our calculator can only be that smart. Okay? It cannot differentiate. It differentiates subtraction and negative. While in math, we know those two are actually have this the same meaning. Okay, so it has to be that negative sign, not subtraction sign. It has to be this negative sign, negative E99. Okay, the upper bound negative 2.53. Okay, the mean is 0, standard deviation is 1. Okay, because it's a standard normal distribution, so the mean is 0, standard deviation is 1. I paste it, enter. 0.00570. This is 0.00570. Let's do more. Let's do more. Let me put Part C here. What is the probability that Z is greater equals to, let's say, 1.75? So greater equals to 1.75. 1.75. So I need the area here. So the interval notation for this interval is 1.75 to infinity. Is it right? Okay, but we don't have infinity, so I will replace this by E99. Okay, I will replace that by E99. So what will happen to our calculator notation? That will be normal CDF from 1.75 to infinity replaced by E99. The mean is 0, standard deviation is 1. So normal CDF from 1.75 positive E99, the mean is 0, standard deviation is 1. That will be 0.04006, 0.04006. Okay, so again, we replace infinity by E99, negative infinity by negative E99. More. How about probability that the Z is between, let's say, 0.81 to, let's say, 1.93? 0.81, slightly less than 1, just to illustrate. This is 0.81 up to 1.93, almost to 1.93. What is the area here? Clearly, from the picture you see, the area must be less than 0.5, right? Because the area for the second half is 1/2, right? Now, this area is less than 1/2. So the probability, as we expect here, will be less than 1/2 as well. Okay, calculator notation, normal CDF, lower fence 0.81, upper fence 1.93, 0, 1. Then on our calculator, this will be, sorry. Oh, what happened? That's normal CDF, 0.81 for the lower fence. Am I at the right note here? Yeah. And then the upper fence is 1.93. The mean is 0. Then deviation is 0.18217. 0.1821666 something, right? I rounded to 7. Okay. So again, I hope you can see that the interval here if you write it in interval notation, is the first two numbers you have here. Okay, and then the last two numbers you have here is the mean and the standard deviation. Okay, let me grab some problem from our textbook for you to work on. Give me a second. Our textbook may still use a table method to compute the probability, and therefore the result from your textbook may be different from the result in our using our calculator. Okay, let me ask you to actually do this one. Number 9 to number 12. Wait a second. I grabbed these pictures from your textbook. Grab this picture from your textbook. Let me ask you to, for each one of them, write the probability notation. Write the probability notation, and then the calculator notation, and then the result from calculator. Okay. Let me ask you to do this, and then let me see more. Then after that, I would like you to do some problems on here. Just paste it here. Okay. So from number 9 to number, let's say just do the odd numbers. I highlight the one I want you to do. So I want you to do number, even number. 10, 12, 20, 24, 28, 32, 34. No, not 34. Yeah, together with your break, this should take you like 6, 7, 8, 9 minutes plus your little break. Let's come back at 9:50. Let's come back at 9:50. At 9:50, we are done with this. Okay, let me say it again. I forgot to record earlier that when it comes to continuous distribution, then the equal sign or not without equal sign in the inequality does not change the way we compute it. Okay, the reasoning is more into the following. Because it's continuous distribution, then remember the probability of an event is equal to the area under the curve of that event. But the thing is, like, for example, in this case, what is the area under the curve for this line? Let's say 1.23 line. Now, because it's one-dimensional instead of two-dimension, then the area of a line is 0. Now, because the area of a line is 0, therefore, either we include or not including equal sign in our distribution for continuous distribution, okay, for continuous, then it won't change the probability. It is not the same with binomial or Poisson, though, which are discrete distribution. Okay, in binomial distribution, in binomial or Poisson, probability of x is less than 3, for example, is equal to probability that x is at most 2. Okay, but in continuous distribution like normal, probability that c less than 3 is the same to probability that c is less than equals to 3. okay, because it's continuous. Now, so coming back here, when we write our probability distribution, does it matter for us to use equal sign or not? Then it doesn't matter. Okay, it doesn't matter. That's the probability notation. How about the calculator notation? That will be normal CDF negative 1.04 E 99 0 1. Let me do it next to it so that I have some space. That will be normal CDF negative 1.04. I use my hand calculator now. I get 0.85083. Number 12. Probability that Z is between negative 1.07 to 0.67. That's normal CDF negative 1.07 up to 0.6701. I get 0.60626. Furthermore, number 20, less than 2.56. Number 20, less than 2.56. That's normal CDF. Let's see what the diagram looks like. Let me steal from here. 2.56 is approximate here. That's my C distribution. Okay, and then I need the area to the left of that. So normal CDF from negative E99 to 2.560. Get 0.99477. Now, please try using your own calculator, okay, to check if the number I get here is true. And especially with the rounding, because the number I get on my calculator for this is 0.994766. But if I round it to 5 decimal places, it becomes 477 instead. For number 20. Number 24, greater than negative 3.05. Oh, is that number 20? Yeah, then number 24. That's all. Probability that C is greater than negative 3.05. Negative 3.05. Oh, wow. So basically the whole one, the whole curve, huh? But we still have some tail here. We still have some tail there. It's just so small that we don't really see. Okay, we have some tail here. Okay. Now, because that tail is so small such that it's not depicted into this graph, then we expect that the probability for that tail will be so small. In the other words, that the probability for this yellow region must be so big. Okay, almost 1. Normal CDF negative 3.05 E 99.01 is 0.99886. 0.99886. Now, with that said, by the way, with that said, then the area of that tail will be probability that C is less than equals to negative 3.05 will be 1 minus that number. That would be 0.00114. Okay, just a follow-up question. That's number 24. Let's do more. Number 28. Negative 2.75 to negative 0.75. 28. Probability that C is between negative 2.75 to negative 0.75. Pictorially, negative 2.75 to negative 0.75. This is clearly less than 0.5 in area later on. This is normal CDF negative 2.75, negative 0.7501. I get 0.22365. Finally, number 32, negative 4.27234. Probability that the C is in negative 4.27 to 2.34. We'll copy that question. Oh, that's very far to the left. So it's negative 4.27 to 2.34. This is equal to normal CDF negative 4.27, 2.3401. I get 0.99, 0.99025. I hope you get the same answer for all this. Okay, any questions so far? Any questions so far? No question. Okay, some notes. Some notes. the first one. The domain of Z is all real numbers, which is from negative infinity to infinity. Okay, so the table that you see here, is actually going indefinitely far to the right, and it goes indefinitely far to the left. Okay, now, however, the area to the right of Z score 5 is nearly 0, and to the left of C score, sometimes we just use lowercase z. By the way, the C score here, I refer to the C score that they use here. This is C score. We call this C score. Not capital C. Capital C refers to the random variable. Lowercase c refers to the C score. Okay. Now, both of them are in the realm of standard normal distribution. Okay. So the C score to the left of C score -5 is nearly 0. Okay. So if you have 5 here, then the area to the right is nearly 0. If you have -5 here, then the area to the left of that is nearly 0. Okay. Let's find the actual value, okay, so that you are convinced that they are so small that it's nearly 0. Okay, so probability that Z is to the right of 5 is normal CDF five E99 0 1. I use my calculator. 5 E99 0 1. I get 2.87105 times E -7. So it's 10 to the -7. In decimal, it means the 2 here, it means this 2 here is at the 7th decimal place. That's 0.00123456 like that. That's how small it is. It's a lot smaller than if we round it to 5 decimal places. It's so small such that it's even smaller than if you round it to 5 decimal places. Okay, by symmetry, of course, then the area to the left of -5 is also the same. Nearly 0. It's so small, even if we round it to 5 decimal places, such that we basically call that 0. Now, so you will see the following. You will see that in practice, when I use my calculator, right, and I want to compute probability, let's say C is less than 1.23, okay? We typed it this way earlier, normal CDF, that's -E99, 1.2301, right? Okay, now this will give you the same result to if you replace this. Now, originally it's -infinity, right? Okay, and we replace that by -E99. Now, I want to say that right now, we will still get the same 5 decimal places if you replace that to -5. Okay, so if I punch normal CDF, -5, 1.2301, it should give you the same number. I'm not saying that this information is important for you, okay? But I'm saying that some instructors, especially the older instructor, when they do their computation, they get so lazy to actually even punch negative E99. They just change it to -5 or -6 or -10. Okay, anything lower than -5, or if it is right tail, anything greater than 5. If they round it to 5 decimal places. Okay? If they round it to 4 decimal places, they can freely change that to -4 and 4 as the cutoff for the tail. Okay, now here I get the result of 0.89065 if I round it to 5 decimal places. Let me write more. This is 10962. If I round it to 5 decimal places, I will get 0.89065. Now, but if I use negative E99, I get 0.89065, 13833. Okay, so even if I round it to 5 decimal places, it will still give me the same result. Okay, so one way to save your negative E99, okay, one way to save that, you can just replace that by, let's say, -10. What I usually do is I replace that negative infinity by -10 or +10 to be more safe. Okay, now if I use -10 instead, then the error will be actually less than the 17th decimal place. Okay, I'm saying that if I change this, if I go even further and I use 10 here, then the area of that tail is less than 10 to the -17, as I remember. I may be wrong, but it's so small, okay, such that the first time you see a non-zero is at the 17th decimal place, you know, okay, such that it's so small that it is very, very negligible already. Okay, however you round it, even your calculator will not detect the difference, basically. Okay, yeah, but of course, Thomas, so in my test, do you want us to use negative E99 or can I use -5? Just write negative E99, it's fine. Okay, but on your calculator, if you are lazy to write that to type that negative E99, just replace that with -5. Okay, now that's for the area of the tail of standard normal distribution once it is greater than 5 or once it is less than -5. Okay, now second, going back to that Z-score. Z-score is a number on Z axis. Okay, Z-score is a number on Z axis. So I use capital C here to denote that this is the Z axis, the random variable, standard normal distribution as a random variable. But the numbers we have here are actually, we don't call that X equals, we call them Z equals with lowercase z, with lowercase z. Now, one of the things that we will do, we are about to do right now, is to find the Z-score associated to a probability. Okay, so for example, the next question is find the Z-score such that the area or probability to its left is, let's say, 0.4. Okay, so basically it means the following. Let's say we have standard normal distribution. Okay, we need to find the C-score here. I don't know what's that. I don't know what is this. But I know that the area to the left of that should be 0.4. Now, remember that this area also represents probability, right? Now, what we had earlier, we have the C-score. We need to find the area. Right now, we go backward. If we know the area, can we find the C-score? Now, let's write the proper notation first. The notation for this situation is probability that capital C less than lowercase z is equal to 0.4. Now, to avoid the confusion, especially if you are not so detail oriented with capital C lowercase c, I will now change this z here becomes k. Okay, I will change that to k so that you don't have hard time to see the difference between capital Z with that k. Okay, now, so this k here is the C-score such that the area to the left is 0.4. Now, the probability notation is given here. So what will k be? What will k be? Okay, k is the C-score, right? Okay, now the calculator notation will be for inverse norm 0.401, where the first number refers to area to the left and these are the mean mu. I'm sorry, the mean and standard deviation. Okay, calculator. It will be here. So you go to that distribution, that will be right below normal CDF, the third option in my tier 84, inverse norm, the area to the left, the area, always the area to the left. Probability to the left, 0.401 paste. Boom. So that's k equals to, oops, k equals to negative 0.25335. Negative 0.25335. Okay, which means actually, yeah, it's between -1 and 0. Okay, now what happened if we change the question slightly different? Find the C-score such that the area to the right is 0. Let's say 0.3. We need to find the C-score. I don't know where's that. Let me just put it randomly. Okay, such that the area to the right is 0.3. Now, translate this into probability notation first. Do not skip my step that I show you here. Please don't. Okay? Please don't. The devil is in the detail, and I'm not teaching you to just use calculator. Okay, I'm teaching you especially because I know if you go to good university later on and you take some courses, they require you to know a good statistic. Okay, now I don't want you to relearn your statistic at that time. Okay, well, very likely you need to relearn it anyway, but the notes that you have, the foundation that you have already learned, should be good enough for you to go back. Okay, yeah, to recover those what you forget that you learned today in my class. Okay, it's a lot harder for you to study things that you never understand in the past. You may think that, Thomas, I just need to pass this class. I don't care about if I'm going to take another stats class or I will use that. Well, then that defeats the purpose of me teaching you stats. The reason I teach you stats here is not only for passing the class. I mean, if your reason is just to pass the class, you take wrong teacher. I'm sorry. That's against my core belief. The reason I teach you math and stats is so that you can use that in your life. Okay, at least according to the curriculum. So if I change everything to just calculator, I downgrade stats class into calculator for stats class. Okay, and whatever number you get has no meaning at all. What for? Okay, no wonder then more and more people complain, more and more students rightly complain that what they learn at school is not applicable to their real life, because when the teacher try to teach that way, you avoid that. Okay, and some teachers just try to make students happy. Okay, unfortunately, no. And trying to make you happy with the job you get, not just you happy with passing this class. And actually, I'm this type of person. Saying that my students learn my stats just to pass the class is actually degrading my student. And I refuse that. Okay, I believe my students is capable to learn. Saying that you cannot learn it so that I have to make it easier is actually saying that you are not capable, you are not smart enough for that. No, you are smart enough. You can do it. Okay, but we only know it if I push you to do it, right? Okay, so what's the notation? Probability that Z is to the right of that K is 0.3. But remember, we can only use calculator once the area is to the left, not to the right. So if the area to the right is 0.3, what is the area to the left of that K? The area to the left of that K will then be 1 minus 0.3, the complement, right, which is 0.7. Now then we are ready to find the K. K equals to inverse norm 0.701. Okay, inverse norm 0.7, not 0.3. No, that 0.3 that you had earlier is the area to the right. You need to change that to the area to the left. 0.52440. 0.52440. Now, from here, then, we may see a couple situation in our textbook later on. Okay, some notation. For example, they say find P47. What is P47, Thomas? What is P47? P47 is the 47th percentile. That is the C score in this case, because we are dealing with a C distribution, right? The C score such that the area to the left is 47%. Okay, then what does it mean? Then you go back to that curve here. I don't know precisely where the P47. I know it's to the left of 0. Okay, let's call that K. We want to find the area. We know that the area to the left is 47%, but we need to find what is that C score. Okay, so probability that Z is less than K equals to 47%. That's the probability notation that we translate from here. Okay, what does this mean? It means this. If the distribution we're dealing with is standard normal, now then the K will be inverse norm 0.4701. Okay, then I will use my hand calculator. I hope you use your own calculator also to try. I get negative 0.07527. Very close to 0. Now, with that said, I would like you to find, do the following. Maybe this one here. Textbook. Let me ask you to do that. Find P10, the 10th percentile. That is the bone density. Don't worry about this. Let me erase that. That is the C score, the score separating the bottom 10% and the top 90%. Let me give you 2 or 3 minutes to do this. Maybe 3 minutes. Okay, let's start. This is basically finding the area, the C score such that the area to the left approximately here. I'm not sure, but I just do approximation. Find K such that the area to the left of that is 10%, which means the area on the right-hand side is 90%. Okay, but we want the area to the left. Probability that C less than K is 10%, 0.1. So K is equals to inverse norm of 0.101. According to my computation, I get negative 1.28155. Okay, now later on when you study from this section, I would like you to do number, let me see. number 9 to number 39. Actually, you can go up to number 43. Suggested homework. Number 9 to number 43. Just do every other or that's good enough. Yeah, I even think if you're really good already, later on you will see this is like a breeze for you. Okay, not hard enough. Not hard enough. Okay, for 6.1 suggested homework is from 9 to 43. Oh, there's actually another notation that I need you to be aware of. They have this, for example, find z, let's say 0.02. This means if you see this notation, so you see you cannot run away from notation, huh? You really need to know what those notations means. Okay, I don't really use this notation, the last one here. I don't really use that. Okay, but it will be nice for you to know. Find C 0.02. This is the C score such that the area to the right, the area to the right is 0.02. Okay, the area to the right. Now, remember earlier we have P, right? P47 is the 47 percentile. The area to the left is 47%. Okay, but if they use lowercase z 0.02, that's the area to the right. So it refers to the K here such that the area to the right is 0.02. That's what it means. Once you know what it means, it's actually a lot easier to write. The probability that Z equals to less than, I'm sorry, not less than, greater than. Z is greater than K is 0.02. But again, we cannot compute if it is the area to the right. We need to modify that for the same K, but now area to the left. Okay, if the area to the right is 0.02, then the area to the left must be 1 minus that. We get the area to the left is 0.98. So K is inverse norm of 0.9801. Okay, inverse norm 0.02, 0.1. I get, I'm sorry, 0.98, 0.1. I get K equals to 2.05375. Okay, that's for standard normal distribution. That's for standard normal distribution. Let me start with normal distribution. Let me start with normal distribution. In case you need to write something down, you know, at the end of the today, at the end of the class, I actually changed these notes into PDF and I posted on the discussion board for the day, right? The discussion board for the day. Okay. Normal distribution is denoted by n mu sigma squared. Okay, so you will see standard normal distribution is actually a normal distribution with mu 0 and variance 1 square. Okay, now for the next 1 hour approximately, I will teach you the same story that I did in 6.1, but this time, this normal distribution is actually a lot more applicable. It's a lot more applicable. Let's say, for example, let x be normally distributed with mean 100 and standard deviation 15. So for the variance position, I will write 15 squared. Okay. Now, normal distribution actually has the same curve. It has the same curve. It has the same curve. Okay. The difference is right now, the mean is not 0 anymore. The mean is 100 in this case. Okay. They will tell us the mean, they will tell us the standard deviation. Because it is not standard normal distribution, then you are not allowed to use capital C anymore. Okay, you are not allowed to use capital C once it is not standard normal distribution. Okay, but the shape is still the same though. The shape is still the same. Okay, the shape is still the same, and you just make it bigger or wider maybe. Okay, or not as tall anymore, but the shape will be very similar to the standard normal distribution we have earlier. Okay, in the first stage, I will teach you just the notation, and you will see, I hope, that the notation is very similar to what we learned earlier. Okay, so for example, if I want part A, find the probability that X is between 80 to 110. From 80 to 110. From 80 to 110. So the mean is 100, right? 80 is to the left of that. 110 is to the right of that. We are interested in finding the area, which is the probability for this region. The area of this region is equal to the probability of that interval. Then the notation will be normal CDF 80 for the left lower fence, 110 for the upper fence. The mean is not 0 anymore. Right now the mean is 100. Okay, and the standard deviation 15. Okay, the mean, the standard deviation. While the lower fence, upper fence are here. Then you use your calculator. In a second, calling that calculator. And that is distribution, normal CDF, lower fence is 80, upper fence is 110. The mean is not 0 anymore. I need to change it to 100 in this case, and standard deviation is 15. 0.65630. That will be equals to 0.65630 by rounding. And you will see everything else is the same to what we learned in the C distribution. Okay, the only things changed right now is that the mean is no longer 0 and the standard deviation is no longer 1. Okay, let's do more. Find the probability that X is less than equals to, let's say, 125. And then let me do it here, part C, or let me ask you to do it. Probability that X is greater than 90. I will do the graph, and I hope you can come up with the calculator notation. Okay, less than equals to 125, so this is 100, 125 is to the right of that, unit the area to the left. That's what I need. Okay, while for the second one, I need the X score. This is the mean is 100, the X score is 90. Okay, and I need the area. So again, for the infinity, you use negative 99, negative E99 for negative infinity. For positive infinity, you use positive E99. Okay, let me give you 2 or 3 minutes to do this problem. This will be normal CDF, lower fence negative E99, upper fence 125, the mean is 100, standard deviation 15. So you use your calculator. I assume you know how to do that already. Okay, on your calculator, you will punch normal CDF, negative E99, comma 125, comma 100, comma 15. I get 0.95221. Well, the second one, part C here, this is normal CDF. From 90, E99, 115. I get 0.74751. The random variable I gave you earlier, the mean 100 and standard deviation 15, usually being used as the first example for non-standard normal distribution. Okay, because it is actually the distribution of a well-known situation in real life. It is known as standard distribution of IQ score. Okay, let me ask you to try doing the following here. I need to enlarge that though, but if I enlarge that, it's too big that you cannot really read it. You know what? Let me do it this way. Give me a second. Let me do it this way. I want you to do it there. So write the probability notation, okay? Write the probability notation, and then calculator notation, and then the calculated result. Then continue with this. Put it next to it. So I would like you to try number 6 and number 8. This is actually still a normally distributed with mean 100, standard deviation 15. Okay, so the same information we have above. 115. Now the one here to find the probability, number 6 and 8 to find probability. And I would like you to do number 10 here. That is to find the X score. Okay, that's to find the X score. That's the IQ score in this case. Each problem should take you approximately 2 minutes. Right now, 10:55. We come back at 11:02. Okay, let me ask you to do this. The probability notation, and then calculator notation, and then a calculator result. Okay. For number 6, let me do it down here. For number 6, that's probability that X is greater than 91. That's normal CDF. (91) E99. The mean is 100. The standard deviation is 15. Okay. I have this habit though. Right before I work on the probability, I usually write the distribution first if it happens to be a special distribution like this. So I will say X is normally distributed with mean 91 and variance 15. I'm sorry, the mean is 100, not 91. With mean 100, with standard deviation 15. Variance, therefore, is 15 squared. Okay, then from there, I use my calculator. Normal CDF 91, E99, 100, and then 15. I get 0.72575. That's for number 6. Number 8. That's probability that the X is between 112 to 124. That is normal CDF 112, 124, 115. I get 0.15706. Finally, for number 10, let me squeeze number 10 here. Okay, let me squeeze number 10 there. Probability, because I want you to see the picture also. Okay, probability that X is greater than lowercase x, right? They use lowercase x. You can use K instead if you like, is equal to 0.1587. So the X score, X will be inverse norm. Oh no, not yet. I cannot do that right away. My bad. I cannot. Why not? Why not? Why not? Why not, Thomas? Because our calculator can only deal with area to the left, not area to the right. Therefore, I need to adjust this a little bit. Okay, take a look on the area to the left instead. That's 0.8413. So the X score will be inverse norm, 0.8413, 100, that's the mean, standard deviation 15. It's inverse norm, 0.8413, 115. Using a calculator, I get 114.9973. I know our textbook may round it to 115, but in my class, don't do rounding. If you round it to 5 decimal places. Okay. Okay. Yeah, that's for number 10. Now, these are all the foundation that we need to work on normal distribution. In real life, we don't really encounter standard normal distribution. We don't really encounter this. Okay, but all the normal distribution that we had earlier actually is the further development from standard normal distribution. Okay, now calculator wise, you will see you don't really need to know standard normal distribution. You just need to know the normal distribution. But in longer run, you will see that's necessary for you to know standard normal distribution. But let's see for now, how do we apply this to real life, AKA word problems? Suppose, for example, I get this one's here. Number 13 to number 18 in our textbook. Number 13 to number 20, they say, but I will do number 14, number 15, and number 18. Okay, the female one. I will do the female questions. Okay, I will focus on the female question. Now, let's see. Use the data in the table below for sitting adult males and females. In this case, we'll deal with females only. These data are used often in design of different seats. For example, aircraft seats, train seats, theater seats, and classroom seats. Okay, now let X be what is this? The length, the seating length of seating back to knee. In inches. Now they say that this for female, for adult female, for adult female. This X is normally distributed with mean 22.7 inches and standard deviation 1. So I will write it this way, 1 square, because that's the place for variance. Number 14. Find the probability that a female has a back to knee length greater than 24 inches. probability that x, that's the back to knee length, is greater than 24 inches. Okay, so in our normal distribution, this 24 is greater than the mean, which is 22.7, right? And you need the area to the right of that though, greater than 24. Then the calculator notation will be normal CDF 24 E99 22.71. Again, you use your calculator to compute this. Twenty-four E99 22.71. That will be 0.09680. That's for number 14. Number 15. Number 15, find the probability that a female has a back to knee length between 22 inches to 24 inches. That will be, let's see what the graph looks like approximately. The mean is 22.7. I need from 22 to 24. This will be normal CDF 22 to 24, 22.7, and then standard deviation 1. Normal CDF 22, 24, 22.7, 1. I get 0.662, I'm sorry, 1, 2, 3, 5, so it becomes 4. That's for number 15. Finally, number 18. Let me do it here. Number 18. So that I still have at least I still have this information. I need that very much. Number 18, find the first quartile. Find the first quartile. The first quartile is the length, the X score that separates the bottom 25% from the top 75%. So we need the area to the left, the bottom, the area on the left to be 25%. Okay, so this is our first quartile. That's our X score. Okay, so what we need is the probability notation probability that X to be less than lowercase x is 25%. And then calculator notation, let me shift that a bit to the left. So x equals to inverse norm 0.25, that's the area to the left, the mean 22.7, standard deviation 1. then I use my calculator. You should try that also to confirm though. Okay, 0.25, 0.25 for the area to the left, 22.7 for the mean, and 1 for the standard deviation. I get 22.02551. So imagine if you're on a train, right? Okay, or you're on a airplane, and then the seat between yours to the seat in front of you. Okay, if they only put it at 22 inches here, then you know approximately 75% of the passenger will complain. The female passenger, approximately 75% of female passenger will complain and say that, oh, you know what, it's way too tight, you know, which is what they are doing actually right now. They try to, I should say on the last 3 years until the beginning of this year, before COVID, okay, they actually try to squeeze that to be small, okay, to hold more passenger, right? And they even told us not to bring anything. If we bring any baggage, then they will charge, right? Okay. Yeah. So this being used, the measurement is being used to find out what is the best number for the distance between one seat to another seat, such that we have less complaint, but at the same time, not taking too much space and cut into the possible profit of that airline company. Okay. Yeah, of course, if they make this larger though, then they will have less seat in the plane, right? Okay. With less seat in the plane, then the average ticket price will be higher. You want the airline to be cheaper, right? Then allow them to cut into the space you use. Okay. Yeah, and the smaller the space they use, the more people they can put in. But the more people they can put in, then the less baggage they can accommodate. Okay, the thing is you cannot have it all. Okay, you cannot have a very comfortable seat and still very expensive, very cheap, and you bring a lot of baggages. Right? Imagine if you go to San Francisco, but then you bring the like 2 suitcases. That's cut too much into this. I'm not trying to defend them. I'm trying to show you the logic why they do such thing. Okay, if you want a comfortable flight, then you eventually need to pay more. Okay, eventually you need to pay more. Of course, to be honest with you, if I go to San Francisco from LA, I rather drive. Why? Once I get to San Francisco, I still need to drive. Right? Maybe. Okay, maybe. But of course, if you have international flight in which you have, like me, I'm from Indonesia, right? So for me to come to fly from LA back to Indonesia, sometimes I transit in Taipei. Recently, I actually transit in Taipei. Sometimes transit in Hong Kong or in Tokyo. Including the check-in process and including the get up from immigration, a total time it takes me is approximately 24 hours. For me to go back to Jakarta in Indonesia takes me approximately 24 hours. Now, if I need to be on the plane for approximately 20 something, almost 20, actually 18 hours in total, right? I don't want to get into a plane whose distance from seat to seat is only 22 inches. I will be yelling I'll be screaming in the plane. Okay, so when they have international flight, of course they will increase this distance from seat to seat distance. Okay, now therefore when they increase the seat to seat distance, of course then the price will be higher, right? Why? Because you're gonna sit in a plane for, let's say, 15 hours, 13 hours to Taipei, right? And then you crunch me into this small space, and I'm considered pretty tall for Asians. So I will be really, I mean, I may not be screaming in the plane, but once I land, I will be so pissed off already, so tired because I have to bend my knee so much. You know, okay, yeah. So yes, there's some statistic come into play when they decide the length of the distance from seat to seat, and they need this information. Okay, I'm about. Oh, hold on, I get a chat coming in. How often do I travel back home? My parents and grandparents and my wife parents uh, from the same hometown. So I usually go back once a year. When I was single, twice a year, like basically in the summer and in the winter. Yeah, and then because I have my wife and with two children right now, I go back only once a year. But this year I have not gone back yet because of the travel restriction. When we were still open, Indonesia closed. Actually, America closed first. America closed first. US closed first. Indonesia still open. But once America opens a little bit, Indonesia's the one closing. When Indonesia and America opens, it's Hong Kong and Taipei the one closing. So it's like you really need for me to go back to Indonesia, we need these three places actually open. You know, okay. Right now, all three already open, but then I'm the one not open. I need to teach. So I plan, if possible, I go back in December. Yeah, because my parents, especially my grandparents, they would be so happy to see me just to visit them. Okay, it's more than just, honestly, it costs a lot. It costs a lot. For one person ticket, it's 1,500. If I go, that's the cheapest of 1,500. If I go back with my wife and my children, it will cost us like approximately $5,000. You know, so there's a chance that this time I go back just for myself. I go back just myself. Anyway, that's for this. Let me give us a long break. A long break right now. Okay, let's start with this application problem. Okay, in exercise 21 to 24, we will use this following information. And the question for number 22A, find the percentage of men meeting the height requirement. And part B, if the Air Force height requirement change, then what is the new height requirement? Okay, both of these two cases here are A and B are for men. So let's see for men. X is, let X be, maybe I define what X be first. Let X be the height of a man. The height will be normally distributed with mean 68.6 and standard deviation 2.8. Let me make it 2.8 squared for the variance. Okay, now then number 22A, if US Air Force requires that pilots have heights between 64 to 77 inches, find the percentage of men meeting the height requirement. So the probability, which is the proportion, which is later on give us the percentage of the height requirement being satisfied. That's 64 to 77. Now we have learned how to compute from this notation to the probability. The new things we learn in this situation right now is actually how to convert or how to translate from the word problems to the probability notation. That's what we are learning right now. Okay, but once you have the probability notation, from there we basically sail through. Okay, we basically sail through. Okay, let's see. And this will be normal CDF from 64 to 77 with mean 68.6 and standard deviation 2.8. calculator. That's normal CDF 64, 77, 68.6, 2.8. That's 0.94844. So the percentage of men meeting that the height requirement will be 94.844%. Part B. Part B. If Air Force height requirements are changed to exclude only the tallest 25% and the shortest 25%. In a second, let me quote this so that we can better visualize that. So we want to exclude only the tallest 25%, 2.5%. So this is 68.6, right? Now we want to find these here so that we exclude only 2.5% the tallest. And exclude only 2.5% the shortest. And so we should be lowercase n. Then what is the cutoff score? Okay, what are the new height requirements? Find that lowercase m and find that uppercase m, such that we only exclude the tallest 2.5% and the shortest 2.5% of men. Okay, let's see. The first part, probability that x to be less than lowercase m. Lowercase m for this, okay, is 2.5%. So m will be inverse norm, 0.025. The mean is 68.6. Standard deviation 2.8. This will be inverse norm, 0.025. Oh, sorry, I punched something. 0.025, 68.6, 2.8. I get 63.11210 inches. While the maximum cutoff will be x greater than capital M is 2.5%, which is 0.025. But I need the area to the left though. Then probability that x is less than m is 1 minus that, the area to the left. Right? So the upper limit, upper fence for the cutoff will be inverse norm 0.975. The mean is 68.6. Okay. So this M will be inverse norm 0.975, 28, I'm sorry, 68.6, and then 2.8. I get 74.08790. Okay. So the new height requirement is between 63.11210 inches and 74.08790 inches. Of course, in reality, nobody will be super strict like that. In reality, they will just say, oh, you know what? Between 63 to 74. Right? You see what I mean? Okay. Yeah, because 63, if you're 63 inches, how to increase yourself by 0.1 inches? Okay, grow your hair a bit longer. Maybe that's way. Or okay, yeah, maybe that's the way. I'm joking, of course. You know, but I mean, in reality, I think they will not be that strict to have. You need to be at least 63.11 inches. Okay, calculation-wise, in my class, you still give me that 5 decimal places. Okay, how do you apply that in reality? Then for every rule, there's exception. People say, right? Okay. I tried not to have those kind of exception in my classroom. Let's go on with number 24. Number 24, they still use the same information there. Number 24. Gulfstream 100 is an executive jet that sits 6 and it has a doorway height of 51.6 inches. What percentage of adult men can fit through the door without bending? What percentage of adult men can fit through the door without bending? So we need the one less than that 51.6. Probability that X is less than 51.6. Okay. This will simply be below. This is normal CDF. Negative E99, 51.6, 68.6. Oh, so the door's height is already less than the average height of men. So there must be more than 50% need to bend. Negative P99, 50.6, 68.6, 2.8. Oh wow, I get this number here. I get this number. I didn't expect this, but I get this number. This is 6.3627 E negative 10. Don't leave this as your answer. Even if this is what you write down, don't leave this as your final answer. You need to repair this. This means 6.3627 times 10 to the negative 10. That's what it means. In other words, if you round it to, if you write it down, if you write it down in decimal, then this 6 here will be at the 10th decimal place. Okay, that would be 0 0.0000, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, the 6 there will be at the 10th decimal place, which if I round to 5 decimal places, that's basically 0.000000. So the probability that a man can go to, an adult man go through that door without bending will be 0. Okay, if that person is an adult, if that man is an adult, then there's no way that person can go through the door without bending. I think it's because the part B is questioning why then the engineers actually don't design the larger door. Okay. But I think it has something to do with the fact that it's a small plane. Okay, such that uh, when they create the door can only open this big. You see? Okay. Okay. So that the plane maybe is a small plane. It's just for 6 people, right? It's just for 6 people. Uh, yeah, I think that's the reason. I think that's the reason. Okay. Definitely, it's not adequate, right? It's not adequate, but the reason they don't design a larger door because that plane in itself is a small one. Okay. Okay. Then let's go on part C. Then what is the doorway height that would allow 40% of men to fit pass through the door without bending? So basically, this is the curve, right? And the mean is 68.6. You need 40% to be able to pass through without bending. So basically find out this case such that the area to the left of that is 40%. Okay, probability notation, probability that x less than k is 40% or 0.4. So k is inverse norm 0.4, 68.6, 2.8. I get, oh, sorry, I found something wrong. I get 67.89063 inches. Approximately 69 inches. No, it won't be. Something more right with this. I copied it wrong. My bad. It should be 67 here. It should be 67. Yeah, I typed it wrong. I write it wrong. I knew earlier was wrong because of this. You see, notice that the average is, the mean is 68.6. Okay. You just need 40%. So you know this K must be less than 68.6. This won't be the answer. This number is greater than 68.6. Okay, and then I look back to my calculator, I found out this, I actually wrote it wrong. It's 67.89 inches approximately. That's for part C. Let's see if we have other problems from our textbook that we can do easily, not too hard. Number 30 is good. Based on the sample result in data sets 3, and we assume the human body temperatures are normally distributed with this mean and this standard deviation. Let X be a human body temperature. This temperature is normally distributed with mean 98.2 degree Fahrenheit, standard deviation 0.62. So the variance is with the square. Now, part A. According to emedicinehealth.com, a body temperature of 100.4 degree Fahrenheit or above is considered to be fever. Okay, 100.4 degree Fahrenheit. Now, it is possible a healthy person have that kind of body temperature without having fever. The question is, if somebody is normal and healthy, okay, what is the probability that person have this body temperature? Okay, so part A, what is the probability that a human body temperature is greater equals to 100.4? Okay, so is 100.4 degree Fahrenheit is a temperature or greater, is a temperature that possibly belong to a healthy person. Now we will see what is the probability if somebody with this body temperature still actually healthy. Now that's usually the case for somebody who just finished exercising, or like in my case, I was one time thought that I was having fever, but it turns out that's because I was actually walk around my complex under quite heavy sunlight. The temperature at that time was actually quite high. So when I came back home, I feel like, oh, do I have fever? You know, when I pass, let's say I pass my wife, and my wife say, hey, you know what, Thomas, if your body temperature seems to be higher than usual, do you have fever? And then I look at that, it's like, yeah, it seems like it's higher, right? But maybe because I came out from just under heavy sunlight, you know, okay? Yeah. In that situation, what you want to do is actually you rest a bit, drink some water, okay, if your body temperature is higher. Okay, I'm not saying that's the only thing you do, but that's the first thing you do, one of the first thing you do. Okay, for those people with babies, one of the things we are very concerned is what happens if our baby's body temperature suddenly increase. At what temperature we will be cautious, at what temperature we will call the doctor, at what temperature we'll need to go to emergency room. Okay, what you don't want to be so panicked such that when we say the average is 98.2, right, and then when you measure your babies it turns out to be 98.4, and all of a sudden you just like, oh, you know what, it's higher than usual, let's go to emergency room. No need. The standard deviation is still more than that, right? Okay, the standard deviation is still more than that. So we want to see under what situation it becomes unusually high. Okay, that is when the probability for that event or more extreme to happen is less than 5%. Okay, so this would be normal CDF 100.4 or greater, 98.2, 0.62. this will be normal CDF 100.4, 9, 98.2, 0.62. I get 0.00019. The number I get from my calculator is 1.93840 times 10 to the negative 4. That's what I get from my calculator. So the one here is at the fourth decimal place. 1, 2, 3, 4. Okay. So with this number, then the probability that somebody's body temperature to be 100.4 degree Fahrenheit or above, given that person is normal, is so small. A normal person with that body temperature will be so small such that if you really find somebody like that, it is more likely that person is actually sick. It is more likely that person is actually sick. Okay, and I think for babies the cutoff is slightly less. It's less than that. I know 100 is definitely hospital already. Okay, I need to go to hospital already if my baby's body temperature is 100. If my baby's body temperature is 99, I think I will be quite cautious already. Okay, 99, 90. I think 99.4 is still okay. It's like I won't fall asleep anymore if my baby's body temperature is 99.4. Okay, or 99.4. I won't fall asleep. I will be awake to really pay attention. Okay, and I may call my doctor already if I need to give Tylenol. Okay, but I don't think that's the emergency room yet. But once it passes 100, I will. Okay, I will explain about that further in the special note right after this. But let's see part B. Now, physicians wants to select a minimum temperature for requiring further medical tests. Basically, at what point we need to be cautious. Okay, now what should that temperature be if we only want 2% of healthy people exceed it? So basically, let's say this is the body temperature normal curve. The mean is 98.2. 98.2 degree Fahrenheit. Now, it is possible that a healthy person have a body temperature greater than 100.4. That's possible. The probability is very small. Now, then then they say, oh, you know what? Let's find out what is the cutoff score such that we will be cautious, okay, and only 2% of people having that body temperature actually still healthy. Okay, what is the probability? The probability that somebody's body temperature more than that K is only 2%. So this can translate into something else. For example, okay, recently, especially since test one, I have a student from West LA College complaining a lot about the way the test supposed to be turned in, and he said that, Thomas, the time you give us is not enough to turn in the test, you know. Okay, and I remember I gave 15 minutes for you to turn it in from the time you're supposed to stop. Okay, so from you stop working on the test to the submission to be completed, it should be 15 minutes. Okay, Now, the thing is, he complained again and again, not only for the test, but also for the quiz submission, that he didn't have enough time. Honestly, for quiz, I flatly say no. Why? Because I give them at least 2 days. Actually, for that one, I give them 1 week. Okay? So the only reason you cannot submit that on time is because you wait until last minute to submit that assignment. Okay, like the one you're supposed to have today, I told you that I already extended until tomorrow evening, right? Okay, let's say the deadline is 8:30, right? And you have since 1 week ago, okay? And if you later on complain that Thomas, uh, I don't have enough time to submit the quiz, then it must be because you purposely not. I'm not saying that it is by accident. No, I'm saying that the only time you don't have enough time to have your submission completed by 8:30 is when you purposely submit that right before 8:30. I mean, not that by coincidence, you purposely do it that way and use that as a reason to complain against me, right? But then, if you don't have enough time to turn it in the last couple of minutes, my question is what makes you wait for more than 6 days? Actually, I can make it 6 days, 23 hours, 45 minutes. Why? And of course, well, I don't have time. Then you tell me then. If you don't have time in this 6 days something, what makes you suddenly have time in the last 15 minutes? You're purposely doing that. I mean, we learn statistic, right? That's a statistic class also, right? Okay, it just doesn't make sense. You're purposely doing that. Now then, what happened with the test, Thomas? I know it's very tight. That's why I tell you in advance that you need to stop 15 minutes earlier. According to my computation, okay, it takes you approximately 2 minutes to stop. Approximately 5 minutes at most, actually, to take the picture and convert it to PDF. Okay, and 8 minutes is enough, more than enough for you to submit that online. As long as it is in PDF. As long as it is in PDF. Okay. Now, of course, if you just take pictures without converting it to PDF, then it will take you more than 8 minutes. But I told you what you need to do, right? If you skip the steps, that's what happened, right? And this person actually complained that he doesn't have enough time, while he's actually 49 minutes late. Now you tell me about it. No, it's unreasonable. It's unreasonable. The only time you can be 49 minutes late is when you purposely go way further after this test. Okay, and then complain, Thomas, I tried to submit the test, but my system, my internet connection is so slow that blah, 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 blah. It's like, hey, when I look at your submission, it's JPG. No wonder the system does not allow that, right? And then he said that he tried to submit that like 1 hour ago. No. I never know, right? Okay, but the fact that you tell me after 49 minutes past the deadline is kind of fishy, right? If you really submit that minutes before the deadline, you should notice that right away. You don't leave it trying to update for the next almost 1 hour and then file and then tell me that, oh, Thomas, something not right with Canvas. Something not right with you. I mean, come on, right? Okay. If you tell me to wait for 5 minutes, I will start calling you already. Hey, are you okay? Right? You make me wait for 10 minutes, I will start to get pissed off. 49 minutes, then you speak up. Something really wrong with you. Okay, you don't even treat your girlfriend, or in his case, you don't even treat your girlfriend that nice. I won't treat my wife that nice. 49 minutes, and you ask me to wait. Something wrong with you. I mean, in my wife's case, very likely because he's sick that I need to wait that long. Then I really say, hey, are you okay? Why do you make me wait that long? Right? Imagine if she actually get to restroom for 49 minutes. Right? Does it make sense? Okay. We try to see what is reasonable. I hope one day somebody really do a research or doing some statistic about how long should somebody stay in the restroom without cell phone. And therefore, okay, therefore we can create the normal distribution on the amount of time a normal person should spend in the restroom doing number 2 without using cell phone. Okay, then from there we can see, okay, what is the probability if somebody passed, let's say past 20 minutes, what is the probability somebody actually using cell phone in there? Why is this why I would like to have this? Because when a student during a test, a student come to me and say, Thomas, I need to go to restroom. I say, okay, do it fast. And it turns out that person takes 20 minutes. Something not right about that person. Okay. But Thomas, what if that person have food poison? If that person have food poison, that person will not start the test to start with. Okay. Yeah. It is impossible that person will have food poison for that 20 minutes. And then once he came out from the restroom, he's fine. No way. No way. We use statistics to catch people lying too, right? The sad thing is, honestly, it backfired to me in the sense that because I know these kind of things, I kind of like detect when people's lying. And when I hear people like that, I just walk away. Well, anyway, coming back to this question, probability that x greater than k to be 2%. But we cannot do area to the right. Let's change it to the area to the left. Less than k, then must be 98%. Right? Less than k, the area of the complement, which is the other side, must be 98%. So k is inverse norm, inverse norm 0.98. Okay, and then it's what's that? 98.2, that's the mean, and standard deviation 0.6. No, I don't think 0.6. I think 0.62. 0.62. So k is equal to inverse norm 0.98. The average is 98.2, standard deviation 0.62. I get 99.47332 degree Fahrenheit. So if that person's body temperature is 99.47, let's say 99.5, then that person has only 2% chance of still being healthy from the body temperature point of view. Okay. Now, such result is called false positive, which means that imagine if somebody with this body temperature, let's say somebody with body temperature 99.473 degree Fahrenheit walk into a hospital. Okay, walk into a hospital. Then what is the probability that person is actually still healthy, but yet the nurses who took the body temperature say that he is sick? Now we call that false positive. Means this person is considered positively sick, but it's actually false. This person is still healthy. The probability is 2%. Okay, so is it possible, Thomas, somebody with this body temperature is healthy? Yes, it's possible, but it is more likely that he's already sick. Okay, it's more likely that person already sick. Body temperature, by the way, is one way we detect the early symptoms of COVID-19. Yeah, that's one of the early symptoms of COVID-19. I think you start having fever first and headache before you have mucus in some people's case. Okay, actually, in most people's case, you start having fever first before you start having some breathing problem. Okay, now actually, once you start having breathing problem, that's already a hospital situation. Okay, so once you start feeling not well with your body and you have your body temperature is elevated, then they usually ask you to, hey, you know what, you need to go check if this is COVID-19, because in COVID-19 case, it's much better if you can actually detect that earlier. Okay, once we start having the breathing problem, then that's already hospitalization. Very likely, you get to ventilator. Which we don't want to be in that situation. Okay. Now that's for this. I can talk more about COVID-19, honestly, but I hope I know some of you, when you turn in your quiz zero, some of you told me not to talk. Try to avoid that. I would like to talk about that from my experience in seeing people around me. Not my family. Not. I'm not talking about my family. I'm actually helping a lot of Indonesians actually sending money to Indonesia. Okay, so this is from America. Just like some foreign people, foreigners, or maybe immigrants already staying in the United States, but they still have family in Indonesia like me. Okay, so from time to time, at least twice a month, I send money to Indonesia. you know and sometimes some people need to send money to America also, and they ask me to help. And of course, this is a person to person help. And then in the last 6 months, I have cases where people ask me, Thomas, you know what, my sister, my brother, my parents, or who in my family actually contracted COVID-19, and I need to send money for that person to stay in a hotel. Okay, and then what kind of can you help me send this money fast, because it happens to be weekend. Right now, today is Saturday, but in Indonesia, it's already Sunday. I mean, it's already Saturday. I mean, this is Friday here, right? In Indonesia, it's already Saturday and the bank closed. So even if you want to send money to Indonesia, it will not reach them. Of course, you cannot send money from Indonesia. Therefore, basically, starting from morning, Friday morning, the bank, there's no transaction possible between these two countries until uh, Monday morning in United States. Okay, but what happens if you have emergency? Then you need people like me to help, right? Now, then when I help them with sending the money, I once in a while also ask about uh, what uh, what kind of medicine or therapy you would you actually your family or your family member who contracted this would need to do. Okay, now I'm sharing this with you not as medical advice. Okay, please don't take it. Of course, you need to go see a doctor. Okay, but most Indonesians, when they have that, they actually take the following: zinc, vitamin C, vitamin D. This is for people who contracted that at very early stage. Basically, they show no symptoms, but they happen to test, and it turns out to be positive and active. Okay, so hey, you know what? In that situation, you need to quarantine yourself. So they go to a hotel, right? They go to a hotel, stay there for 2 weeks. Okay, these are the basic ones. Sometimes they were prescribed with some antibiotic or some other antiviral. Okay, but in Indonesia, what I know, couple of my friends, actually doctors, they use HCQ, hydrochloroquine, quinine. Okay, and then on the top of that, they also take sometimes antibiotic. You need to go get it from doctor. In Indonesia, in America, this is not free. I mean, it's not freely traded. You cannot just go to CVS and buy hydro. I'm sorry, we call it HCQ, hydrochloroquine. And then the antibiotic is always from the doctor. Different people prescribe differently. But for Indonesians, we have more things. We have the first one is betel leaf. Betel leaf. In Indonesian, they call that daun sirih. You boil, let's say, the 3 leaves. You boil it from 5 glasses to only 1.5 glasses left, and then you drink it hot. You drink it really hot, basically the temperature of when you drink coffee, like how to say that? If you want to have a very good coffee, they say, you know, the water that you pour into the coffee has to be like nearly boiling. Okay. Now, of course, you don't drink it right away, but you drink it when it is basically still very hot, almost burning, almost burning. Uh, Whoever actually in this situation ends successfully is recover. All of them say that whatever you drink, it has to be very hot. It has to be very hot. Now, there's another one, ginger. So you boil ginger. Basically, you boil it from 5 glasses to 1.5 glasses. So the same. Okay. The ginger, you may want to actually chop it first, right? Okay, so that the ingredient can get into uh, the boiled water easily. Okay. Now, I was told that both of these has uh, they call that blood thinning effect. So this may not be good for those uh, who has issue with how to say that. If you are taking a medicine for blood thinning, this will make your blood way too thin and cannot coagulate. You know, like if you have bleeding, then the bleeding will not stop. Okay, so this is only for those people without precondition, happen to contract that and try to prevent the COVID-19 to get worse in you. Okay, but again, this is when you catch it very early stage, and of course you need to consult with your doctor. Now, all of these people also told me that they actually put themselves uh, under the sun, so heat up your back. So they actually do going to the top of the hotel where they stay, okay, and then basically put themselves under the sun, and the back is the one on facing the sun. Okay, so you face down instead. Okay, I think it has something to do with the fact that they need some infrared to heat up your lung so that the mucus is not uh, getting thicker. So the turmeric effect of ginger, in which it's making your mucus not clumping. Okay, is actually the one that you need. Okay, but then for the rest, they say the body can actually handle it. The hard part is really how to make the mucus not clumping and prevent you from breathing freely. That's the worst situation. Again, what I mentioned here are from those people who went through the situation and they were healthy, so all of them without precondition, okay, they showed some symptoms, tested positive, and it was active, the virus was active. And what they did was, when they quarantined, they actually took this, of course, the antibiotic from the doctor. Okay, but all of them was prescribed this. For HCQ, it depends on the doctor. Some doctors don't want to use that. Some doctors actually allow to use that. But in Indonesia, we use this. HCQ is malaria medicine. Originally a malaria medicine. And Indonesia is tropical country, and we have quite high incidence of malaria in some places. So HCQ in Indonesia is made basically free access. You can buy it basically at most pharmacies there, without, almost to the point of without doctor's prescription. Well, it's Indonesia, so there are times that we have a law that, but nobody followed at all. Okay, I hope my sharing here helps you. Okay, at least at the very beginning, what you get, what you do. Betel leaf, as I know, is not easily, you cannot easily find it. You can only find it, and I heard, in Hawaiian supermarket. Most Asian supermarket don't have it, but Hawaiian supermarket has that. Okay, now ginger, on the other hand, is something you can get easily pretty much every grocery store. Okay, so most of my American friends who contracted COVID, and I happen to know, most of them use ginger. But Indonesia have a lot of betel leaves, and they say betel leaf is actually more effective when compared to ginger. But in both cases, they drink a lot. They basically use uh, the ginger to avoid the mucus to be clumping. Use the water, very hot water, also to prevent the mucus from clumping. You know, like if you have mucus, right? Let's say you have some mucus. It doesn't have to be COVID-19. What the doctors tend to tell you to drink is hot water. Why? Because hot water actually make the mucus thin, right? Okay. And the third one is they drink a lot. Why you need to drink a lot? Because drinking a lot make you pee a lot, right? And it reduce the amount of virus in your body. You basically flush it out. Okay, that's not the right term, I know. Okay, but that's what those doctors say. Well, by drinking a lot, you flush the bacteria out. Okay. Well, anyway, let's go back to school. Go back to our class. In no way what I tell you here represent any doctor's advice. And of course, every time you feel not healthy, if you have some symptoms of COVID already, fever, that's the first one. A fever can be anything else though. Okay, can be if you have just you have flu, or even if you just simply have cold, it is possible you have fever. Okay, even though as I know, cold may not have fever. Uh, but fever can be a symptom for a lot of. Basically, fever is the symptoms where our body try to fight some virus or bacteria. Okay, and one of the way is to increase the body temperature, and because higher body temperature will uh, help fighting the bacteria. Okay, just like us, like if you heat up, the reason we heat up the food is actually to kill the bacteria, right? Okay, uh, so having fever is one symptoms that our body is fighting foreign things coming to into our body. Okay, what else? I was told that you may have some muscle spasm in some people, change of taste. When you eat something, you suddenly cannot taste it, cannot feel salty or even smell it. Okay. Now, coming back to our class, I want to write it as notes right now. First one is about the issue of usual interval. The usual interval is twice standard deviation away from the mean. Twice standard deviation away from the mean. Okay. Now, if we look at the standard normal distribution, so our standard normal distribution, okay, and you go from -2 to +2, the C-score. The probability here will be 95%, approximately. It's supposed to be supposedly -1.96 or 1.96. But for sake of simplicity, they just make it twice standard deviation. So you will see a probability between -2 to 2 will be very, very close to 95%. Which implies the area, the tail area outside of this interval is less than 5%. Okay, this is 0.9544450. Okay, so the area, it implies the probability to be outside of -2 to 2 is 1 minus that. That's 0.04550. Okay, that's where the twice standard deviation away from the mean coming from. Now, implicitly, I already say that the C-score actually also represent the C-score actually means the number of standard deviation from the mean. The number of standard deviation from the mean. Now, suppose for example, I have X to be normally distributed with mean 100 and standard deviation 15. Okay, and let's say we find an IQ score. Let X equals to, we find a data which is 125, for example. And what is the C score? What is the C score? This is the mean, 100, 125 here. Okay, now the thing is, the distance is 25, right? Now this 25 is how many standard deviation from the mean. Then the number of standard deviation from the mean will be 25 divided by 50. Okay, that's 5/3, that's 1.67 approximately. Okay, so the C-score you will see is has this formula. Whatever the score minus the mean over the standard deviation. Okay, so the C-score here will be 125 minus the mean over the standard deviation 15. Z is 1.66667 in decimal. Okay, so a faster way to know if somebody's IQ score, for example, is usual or unusual, a faster way is to see what is the corresponding C-score. Now, somebody with IQ score 125, for example, even though it's above average, but because the C-score is only 1.6 something, it's not passing 2, it's not greater than 2, then this is not unusual. This is not unusual. Okay? The chance for us to find somebody with IQ score 125 or greater is actually more than 5%. Okay, so instead of computing the probability, we look at the C-score. Okay, using the same idea, let's say, for example, what if somebody's IQ score is actually 140? Is 140 considered higher than usual? Okay, then look at the C-score. Look at the C-score, 140 minus the mean divided by standard deviation. That's 40 over 15 reduced by 5, that's 8 over 3, that's 2.66667. That's greater than 2, right? So consequently, IQ score 140 is unusually high. Is it considered smart? Yes. Is it considered genius? As I know, it's not yet. The way they define genius, as I know, is if your IQ score more than 145, which is 3 standard deviation away from the mean or more. In other words, if the C-score is greater than 3. Okay. Now, going back to that usual interval, there is something called far out, the terminology far out. You don't find this in your textbook. You don't find this in your textbook. And the far out case is a case that hardly happens, but it does happen. It does happen. Okay, what is far out? Far out is the event more than 3 standard deviation away from the mean. From the mean. More than 3 standard deviation from the mean. Or another way to translate that is the event whose C-score, whose Z-score is more than 3 or less than -3. So let's say this is the C-score equals to 0, -3 and +3. Okay. Then we say it is a far out if it is greater than 3 or less than -3. That's what we mean by far out. So me and some of my friends at, if you happen to know Mr. Hidalgo in the tutoring center, Mr. Hidalgo, Mr. Huang, we are all instructors usually teaching statistics. Okay, and when we say this person is very smart, and we'll say, oh, you know what, his C-score is greater than 2. If that person is so smart that it's not just basically very likely somebody who already have a degree in math and pretending to take a statistics class at ELAC college, then we say, oh, that person's C-score is 3, more than 3. Okay, when everybody like getting 40, 50, that person getting 90, you know, okay, and that person is considered far out. Okay, that's just an example though. But the terminology far out actually is out there. Okay, not used a lot because it doesn't happen that much. It doesn't happen that much. In fact, even twice standard deviation away from the mean, for which we use the term unusual or outlier, it's not used a lot, but we do use it. Okay, like less than 5%, right? But far out is even less than 0.3%. Why? Because the probability for this to happen, the effect for this to happen, is less than 0.3%, empirically speaking. Okay, less than 3 out of 1,000 people having that situation on average. Okay. Now then, with that said, let me give you some instinctive example. Suppose, for example, I tell you that the average of your test one, I make up numbers. This is not the real one. Okay, I just make up numbers. Let's say the average for your test one is 65, and standard deviation is, let's say, 12. Okay. Uh, and suppose your score is approximately normal, then what can you say about what do you think? What is your opinion about somebody who get 90? 90. When somebody getting 90, do you think that person is actually above average? Okay, then we take a look. What is the C score? That's 90 minus 65 over 12. That's 25 over 12. Look, I said 12, that's slightly more than 2, right? That's 2 and 1 over 12. That's slightly more than 2. But we can say this person already unusual. Okay, this person already unusual. This person is actually doing better, significantly better than average students in this class. But at the same time, if you have somebody getting, let's say, 20, believe it or not, you can say the same thing about this person. 20 minus 65 over 12. That's negative 35 over 12. That's actually negative 211 over 12. That's less than negative 2. In fact, this person almost negative 3, right? The C score is almost negative 3. So this person is almost far out. So judging from the mean and standard deviation is 12, then the person who will get 20 must get it because he or she didn't do what he or she is supposed to do. Like, for example, this person supposed to study 1 or 2 weeks, starting from 2 weeks before the test, or the latest 1 week before the test. This person very likely just study 1 day before the test. Okay, but Thomas, is it possible that person just simply uh, not capable to learn higher education, going to college? I don't think so, though. I don't think so. Why? Because for you to be able to survive, how to register being a student at ELAC college, it's actually quite complicated already. Okay, the fact that you can be a student at ELAC college is very, very likely. I can say more than 99% of a chance that you are actually normal. You are not at the place where you are intellectually challenged. No, I don't think so. I don't think so. And I refuse to think that way. Okay. But so the fact that you can get so much less than the average, so many standard deviation away from the average, it must be because you didn't do what you're supposed to do. Okay. Now, and if that's the case, it means it is quite easy to fix though. Just do what you need to do. Okay. Just do what you need to do. Okay. Now that's how we use this standard deviation, the mean and standard deviation, to get the C score, and using this C score to kind of like pinpoint where is this number, where is this data located in the whole distribution. So this is, let's say this is 65, the mean. You add 1 standard deviation, that's 77. Add another 1 standard deviation, that's 89. 1 standard deviation less, that's 53. 1 standard deviation less, that's 41. So whoever get more than 89 or less than 41 in this situation is considered unusual. Unfortunately, in your test one, I have more down here. More down here. So they are unusually bad scores. But I don't want to, and I refuse to say that these students are just stupid. You know, no. I refuse anyone to call my students stupid. No way, no. It must be because you didn't do what you're supposed to do. Okay. And if you are one student like that, please study well. Your next test is basically your last chance to improve your grade before the course becomes a lot harder. Okay, and that's the reason I actually went over one of my old tests. And of course, please study more for your other tests. Okay, now uh, this 6.2 normal distribution provide us a big view of what can happen, how we can do statistic in faster way actually once we understand the C-score. Okay, once we understand the C-score. Right now it's almost 1 o'clock. Let me give you like around 10 minutes break. We come back at 1:05, and then I will give you a small introduction into 6.3. Okay, we will do 6.3 sampling distribution, which also called sample mean distribution. Now, for this section, our textbook going over a lot of examples, as I know. Okay, and a lot of, not only our textbook, a lot of other textbook also going over a lot of examples though. But instead of doing a lot of examples, let's focus on one example and understand it very, very well. Okay, and that's the part that is not easy. Let me start with the following. Let X be a random variable with possible outcomes 4, 10, 16. And it's equally likely outcome. Now, when we say equally likely, it means the probability of getting 4, probability of getting 10, probability of getting 16 are all the same. Therefore, if we construct the frequency distribution, the probability distribution, then probability of getting 4 and 10 and 16 are all the same, which must be what? I wonder how many of you following me right now. If they are equally likely, the total has to be 1, being shared by 3 possible outcomes. Probability for each is 1/3. Now let's compute what is the mean and variance of this distribution. Okay, so we are interested to find the mean of this random variable and the variance of this random variable. Okay, we'll first do the first extension, dx. 4 times 1/3 is 4/3. This is 10/3. This is 16/3. The sum is 30/3, which is 10. So the mean of this distribution is 10. How about the variance? Then I need to do the second extension. First is the first column of this second extension is x squared, and then the second column for this second extension is p times x squared. This is 16, 100, 256. They all come from here. So 4 squared is 16, 10 squared is 100. 16 squared, 256. Okay, that's where those come from. Now then the last column, probability multiplied by x squared. That will be 16 over 3. Okay, and so on and so forth. This will be 100 over 3, 256 over 3. That is 372 over 3. That's 100.4. Now then the variance is the sum of px squared minus the square for the sum of px. The sum of px squared minus the square of the sum of px. That's 10 squared. That's something you're supposed to know already, right? Okay. At least you must see this in your test next week, for sure. Now, the thing is, we will derive a new distribution from there called a sample mean distribution, or our textbook called that sampling distribution. Okay, suppose from this X distribution, okay, we will get sample of size 2. Now, from X, get all possible samples of size 2. Of size 2 with replacement. Which means you will sample from this 4, 10, 16 twice, and you may get repeated result. Okay, get sample of size 2 with replacement. So what are the possible outcomes? The possible outcomes are 4 and then 4. That's one possible pair. Okay, 4 and then 10, 4 then 16. That's if you get 4 first. If you get 10 first, then it's 10 then 4, 10 then 10, 10 then 16. In total, you know, you will have 9 possible outcomes. Why? Because the first outcome, you have 3 choices. The second outcome, you have 3 choices too. Okay, so these are all possible outcomes of sample of size 2. So if you are doing sampling of size 2, these are the possible outcomes. Now you will see the probability for you to get 4 and then 4 again, right? Probability of getting 4 and then 4 again is, probability of getting the first 4 is 1/3. Probability of getting the second 4 is 1/3. Probability of getting any outcomes here, 10 and then 16 is, probability of getting 10 is 1/3. Probability of getting 16 is another 1/3. Okay, so you will see the probability of getting any one of this sample, probability of getting any one of this sample is equals to 1/9. In other words, it becomes equally likely also. Okay, it will keep the equally likeliness that we have since the beginning. And you can see if I add them here, the total will be 9 over 9, which is 1. Okay? Now, the thing is, you see, you have, when you do sample of size 2, then you get a pair of numbers, right? You get a pair of numbers as your sample. You get a pair of numbers as your sample. Can we find the mean of those samples? For each sample you get, find the mean. So let's say for the first one, 4, 4, you get a sample of 4, 4. What is the mean? Denoted by x bar 2. X bar for the mean, x bar sample mean. The subscript 2 represent the sample size of size 2. I mean sample mean of size 2. Okay, so the sample mean here will be 4 plus 4 over 2. That's 4. For this one, for example, the mean for that outcomes is 10 plus 4 over 2, that's 7. I will do the same for all of this. Okay, add divided by 2. Basically, I look for the mean of the pair. Okay, this is 7, this is 10, this is 10, this is 13, this is 10, 13, 16. Now, so you can think of it this way. This is now our random variable. This is now our random variable. What is this? This is the distribution of sample mean. This is your sample. This is the mean of that sample. Okay. In other words, your x bar 2 now, the mean of sample of size 2 may be 4, 7, 10, 7, 10, 13, and 13, 16. Okay, those are the possible outcomes for the mean of any sample of size 2 that you get from this 4, 10, 16. Of course, we can simplify this distribution. We can simplify this distribution to only saying this is 4, 7, 10, 13, 16. We can just say it that way, okay? But the probability of getting 4 will be, the probability of getting 4 x bar 2 is 1 over 9. The probability of getting 7, there are 2 of them to get 7. Right, that's 2 over 9. The probability of getting 3, of getting 10 is 3 over 9. To get 13 is 2 over 9. And to get 16 is 1 over 9. You can see it that way too. You will see the total probability is 9 over 9, which is 1. Now, I will just use this one. You can use this new distribution if you like. Okay, you can do that. That's okay, don't worry. Okay, but let me just continue from what I have here. I want to find px bar 2. Basically, the probability multiplied by the random variable. The probability multiplied by random variable. So 4 over 9, 7 over 9, 10 over 9, 7 over 9, 10 over 9, 13 over 9, 10 over 9, 13 over 9, 16 over 9. And I get those numbers from multiplying this and this. Multiplying this and this. Multiplying this and this to get that. Now, this is where it gets more confusing. When I add this, when I add these numbers here, we get 90 over 9. Oh, to add those numbers, okay, not hard. Okay, but what does it mean? What does this 10 represent? this 10 represent the expected value of x bar 2. So the expected value of x bar 2 is 10. Or we usually write it as the mean of x bar 2 is 10. Is it okay? Where is it confusing, Thomas? How do you read this notation and interpret this notation? How do you read that? That's the mean of sample means of size 2. When you do sample means of size 2, okay, you have these possible means. You have these possible means. Now, what is the average of those possible means? What is the mean of those means? Okay. Thomas, you are so mean. What do you mean by the mean of those means? Yeah, the word mean here has a lot of meaning, right? But what we do here is the mean of sample means. Of all possible sample means that you get, what is the average of those sample means? That's what we mean by the mean of sample means. Okay, our textbook try to avoid that confusion by calling this the mean of sampling distribution. That's what our textbook call it. Okay, now you can call it that way if you want. That's actually one of a formal name for this. Okay, that's the mean of sampling distribution. I just tried to clarify that, and therefore it leads us to possible confusion of the redundancy of using the word means. But we have we have 9 possible sample means. Okay, to be more precise, only 5. But from here, from this list, we have 9 possible sample means. Okay, then what is the mean of those sample means? The mean of those sample means is 10. Now, how about the variance of those sample means? To find the variance of those sample means, I need to first create the second extension. Okay, so I need to find x bar 2 squared and px bar 2 squared. From that x bar 2, you square. Okay, so this will be 16, 49, 149, 100, 169, 100, 169, 256, and then multiply by the probability. Each is 1/9. So I'll just multiply each one of them by 1/9. Which, when you add them, this is actually best done using Excel. if I add them, I will get 1008/9. You can try complete that yourself, okay? But when I add them, I get 108/9, which turns out to be a nice number, 112. So what will the variance be? The variance of the sampling distribution, the variance of sample mean distribution, or the variance of sampling distribution will be 112 minus 10 squared, which is 112 minus 100 or simply 12. Now, I want to tell you that 12 is actually coming from the 24 we have earlier divided by sample size of 2. The 24 that we have earlier divided by sample size of 2. Now, let me summarize what we have done here, and we will apply the same idea without any further computation, but just come up with the theorem or sampling distribution of the following. The summary. Let's say I have a random variable distributed in a way that the mean is mu and variance is sigma squared. To clarify, let me make it mu sub x and sigma squared sub x. Now, the consequence, if you do sampling with size n, if you do sample with size n, then the sampling distribution, the sample mean distribution, will be distributed in a way that the mean of that sampling distribution is the same to the mean of the underlying distribution. The mean of this sampling distribution, in our example, it was 10. Okay, is the same to the mean of the underlying distribution, which was 10. The variance, however, is equal to the original variance, the variance of the original, the underlying distribution, divided by the sampling size. The mean will be the same. The variance will be divided by sample size. Okay, let's see. So to summarize what we had earlier, going back to example 1, if we summarize that, our x has the mean equals to 10 and variance equals to 24. Then what can we say about our sampling distribution of size 2? The sampling distribution of size 2 will have mean the same, but the variance will be the original 24 divided by 2. Where do you get that 2 from, Thomas? From sample size. Oh, so what happened if I do sampling of size 3? Well, as you can guess, if I do sampling of size 3, the x bar 3 will have sample means the same, yet the variance now divided by 3. Okay. And we can go further. What happened if, in example 2, let's talk about IQ score. X is normally distributed. It doesn't have to be normal, actually. With the mean is 100, and then the variance is 15 squared. The standard deviation is 15, right? Now, suppose then you grab 5 people. You randomly select 5 people, and you want to find how will these 5 people's IQ score be distributed. For now, we will say that the sampling distribution of these 5 people, IQ score of these 5 people, will have mean equals to 100. And the variance will be that 15 squared, the original variance, the variance of the underlying distribution divided by 5, the sample size. Okay, now it's not about the 45. You can just use calculator to get that 45. Okay? It's about how do you get that 45. That 45 comes from the original variance, the variance of the underlying distribution divided by the sampling size, the sample size. It is just that simple. It is just that simple. Now, next week after your test, we will go on, continue from here to another building block of statistics called central limit theorem. If there's any theorem that is so big in statistics, that's central limit theorem. It gains such a big name again, such that we can say the following. We can say the following. The bridge between probability going to statistics is actually being built using 2 stones. First one, normal distribution, standard normal distribution. The second stone is central limit theorem. Okay, so probability exists without statistic originally, okay, in my opinion. But then from statistic, how we get into statistic, that's actually having these 2 building blocks, standard normal distribution and central limit theorem. Okay, now I will just stop here. See you next week. Our test will start from, what time is our test again next week? Give me a second, let me see in my announcement. As I remember, I actually make it start at 8 o'clock somehow, I think. Last time, is it right? Let me see my first announcement. Yeah, I said that I will post the PDF of the test at 8:05, and then you have 2 hours to work on that. 10:05, you should stop working on that, and then start uploading it. Okay, it has to be fully uploaded by 10:20. But so we need to do the check-in. We need to do the check-in a lot earlier. Yeah, we need to do the check-in a lot earlier because you will be Zoom proctored, right? So I need you to actually go online, let's say around 7:45 if possible. Okay. Or do you prefer me to start the checking in, let's say at 8:15? Let's decide at the time. Let's decide at the time. Okay, but for now, my standing is we still follow the first announcement. Okay, the check-in should be done before 8:05. Don't wait until last minute though, because I have like at least 20 students in this class still active. So I need to check your ID and make sure your camera is actually done correctly, right? Okay, and then once most of you already done with the check-in, then I will post the test. Okay, that's for today then. See you next week.
Thank you.
You're very welcome.